This is our fourth video on quantum physics for AP Physics 2, so just the beginning, the basics of quantum physics. In this video, I will try to solve some more problems or questions for you for practice, and also to get through some of the photoelectric effect problems. If you find quantum physics or modern physics problems when you're studying for AP exam FRQ type questions, just let me know which questions they are, and maybe I can record some more videos for you to, not only just for you to see, but for everybody else to see in the classroom as well. And let's jump into video number 4. So despite of the popularity of Einstein's theories of relativity and his studies on black holes, Einstein's Nobel Prize in Physics was actually awarded for his discovery in photoelectric effect. And this discovery revolutionized our understanding of the world around us. But what is photoelectric effect? So Einstein stated that light can be both wave and particle, and this phenomenon known as wave-particle duality of light is the fundamental for all quantum mechanics and has influenced the development of many electron microscopes in solar cells. So when the light of a certain frequency or a certain threshold hits the metal surface, an electron, like we saw in the previous videos, that was previously bound in the metal atoms is knocked out loose, and each particle of light called a photon collides with electron, only one electron, and uses some of its energy to pull out electron from the metal, like we saw in the previous video, where you have work function energy needed to pull out the electron, and the rest of this energy is transferred to the free roaming or negative energy called the photoelectron energy. And so why this phenomena is happening, many scientists did not have an answer for that question, and many scientists tried to figure out the explanation for this phenomena. So the photoelectric effect was first observed in 1880s when Hendrik Hertz, during experiment with his spark gap generator, noticed that there is a spark generated between two small metal spheres, and he wanted to know the explanation of why this spark has occurred. So not only Hendrik Hertz was wondering about this phenomena, but also J.J. Thomson showed that this increased sensitivity was the result of light pushing on electron, and a particle that he discovered in 1800s as well. What they came up with the conclusion is that all electromagnetic radiation transforms energy, and it is quite easy to imagine that this energy being used to push tiny particles of negative charge free from the surface of the metal. And from the surface of the metal, because these particles are not all that strongly confined in the first place, like in the outer shell of the atom. So the new era of the modern physics started, and the new discoveries started to come up. And so Hertz's assistant Philip Leonard also was helping Hertz, and he used metal surfaces that he cleaned first and held under vacuum so that the effect of the light will be studied and no other side effects would cause other reactions or oxidations. So the metal sample was placed in a glass tube with a second metal plate mounted at the opposite end, and the tube was then positioned so that the light would only shine on the first plate, and made it photoemissive material under their investigation. And they called this tube photocell. It was formally named photocell or electric eye informally. So Leonard connected his photocell to a circuit with a variable power supply a voltmeter and a microammeter, and showed that the current would occur. The current would occur when the light was emitted to the first plate, metal plate. So that proved that the light could bombard the metal plate and emit the electrons from the surface. This current, sometimes called photoelectric current, was measured by the microammeter, very sensitive galvanometer that would detect the microamps. And when they low down the power supply or the voltage of the source to a very small potential, they would notice that the current would stop, and so the light would still be shining, but the current would stop. When they increased the voltage, then the current would resume to increase as well. So they started to change the potential until they found the potential at which the emitted electrons could not make from one plate to another to cause the current. And this potential at which this occurred is called the stopping potential. And it is the measure of the maximum kinetic energy of the electrons emitted from the surface of during this photoelectric effect. I found this amazing picture from physics.info, and it shows the kinetic energy of different metals emitted and how much kinetic energy you see different threshold frequencies, the frequencies at which the electrons would be emitted from the surface, like potassium, beryllium, or titanium. And then you see that every single one of them will have different kinetic energy and different threshold frequency. So in the formula that we're going to be using, it's the formula that you have seen earlier. You have the stopping potential energy that is needed to stop the electron equals 2, and you have the voltage is equal to the work over the charge. So they rewrite as energy is equal to the voltage times the charge. So right here you have the electron charge times the voltage, or electron volts. And then you have, that's the maximum kinetic energy of those electrons, and that would be the energy of the photon minus the work done to pull out the electrons from the surface of the metal. And that energy, the maximum kinetic energy, also is using the formula that we already know, the maximum kinetic energy with the velocity, the maximum velocity of the electron being pulled out. Okay, so I'm going to jump to the problem solving so we can go over some problems before the video is over. In this question, they ask you to calculate the de Broglie wavelength of the electron moving at the velocity that they give you. And I need to convert this velocity into meters per second, which is going to be 3×10⁷ meters per second. And to calculate the wavelength of the de Broglie's wavelength, I can use de Broglie's formula. With the wavelength, which is lambda is equal to h, the Planck's constant, divided by the mass times the velocity. So I have h, which is, I have to put everything in joules times seconds, so it's going to be 663 10⁻34th divided by the mass of the electron, 911 10⁻31st, and the velocity is 3×10⁷. So that gives me the Broglie wavelength is equal to, and that would be the wavelength of an electron moving at this velocity. If it had the light wave properties, it would have this wavelength. And I get 243 nanometers. For the next question, they say electrons in a diffraction experiment are accelerated through a potential difference of 200 volts. And what is the de Broglie's wavelength of these electrons? So we know that the kinetic energy of the electrons, the maximum kinetic energy would be equal to 1/2 mv squared. And then that energy is also equal to the charge times the potential difference between the electrodes. So we can calculate our velocity. So the velocity is going to be 2 times the charge of the accelerated electrons times the voltage divided by the mass, and all of that square rooted. So we get the velocity is equal to, plug in the numbers for all the values that are given, and that will give me the velocity number equals to 8.38 10 to the 6 meters per second. And they ask me for de Broglie's wavelength. So the wavelength is going to be equal to the Planck's constant divided by the mass times the velocity. So I have the Planck's constant 663 10 to the negative 34th divided by the mass, which is 911, 10 to the negative 31st times the velocity, which is 838 10 to the 6. And that gives me the wavelength equals to 0.087 nanometers. In this question, they say a physicist is trying to determine the identity of a metal by experimentally finding its work function and then comparing the experimental value to a list of known values. If the physicist shines light with a frequency of 410 to the 15 hertz on the metal and records an electron speed of 910 to the 5th meters per second, what is the work function of the metal? So we know that if you have a metal and if the photon is coming with some energy, so the energy of the photon is equal to Planck's constant times the frequency, there's going to be some energy used to pull out the electron. And then wherever energy is left is going to be the kinetic energy of the electron. So the kinetic energy of the electron is going to be 1/2 the electron mass and its velocity squared. The velocity is given and the frequency of the photon is given. And I'm trying to figure out how much work energy is required. So I have the energy that a photon has is equal to the work function plus the rest of the energy, which is the kinetic energy of the electrons, or the maximum kinetic energy of the electrons. So I have the Planck's constant times the frequency that is given is equal to work function plus the kinetic energy of the electron. Now, if I plug in the numbers, I will have here is the energy of the photon with the numbers plugged in. Then I have to find the work function. So here is the work function. And here is the kinetic energy with the numbers plugged in. 1/2 the mass times the velocity squared. So that is 9 squared 10 to the 5th, and also squared. So now if I calculate this, I will get that my work function is equal to, so the work function is equal to 22.83 10 to the negative 19 joules. And if I want to convert this into electron volts, I have to divide it by the electron charge, which is 1.6 10 to the negative 19. And that will give me the value in electron volts, which is 14.27 electron volts. So you could write your answer in electron volts, or you can write your answer in joules, and that would be the work function needed to pull out those electrons from the surface of this specific metal. In this question, they say an atomic transition takes place between the energy level 3 at where the energy is negative 1.2 electron volts, the energy needed to bombard the electron out of the atom, to the ground level where the energy level is negative 5.4 electron volts. That's again the energy needed to for the electron from the ground level to jump out of the atom. And then what is the wavelength of the photon that is during this transition. So what we want to do is to figure out how much energy is lost when the electron is jumping from the energy level 3 to the energy level 1 to the ground level. So the difference between these two energies will give me how much energy photon is emitted, because that's how much energy is lost. So that energy is going to be equal to the difference between these two energy levels. So if I subtract them, 5.4 minus 1.2 gives me 4.2 electron volts. To convert this into, because they asked me to find the wavelength, so I have to convert this to joules. So I'm going to times it by the charge of the electron, so that is 1.6 10 to the negative 19, and that will be my energy in joules. And this energy can be expressed as the Planck's constant times the frequency of those photons emitted, or the Planck's constant times the speed of light over the wavelength. So let me multiply this number to see what that number is equal to. So I have 672 10 to the negative 19, and I'm gonna plug in, I could keep it after all in electron volts if I use Planck's constant in electron volts. So because I converted this number, whole number, into joules, I'm gonna plug in my Planck's constant in joules. So that is 663 10 to the negative 34. Then I have 310 to the 8 and the wavelength. And then we have 672 10 to the negative 19. So from here I can find the wavelength is equal to, the wavelength is 296 nanometers. This question, they ask you how much energy is contained in a particle that has a mass, and they give you 1 microgram. Micro means 10 to the negative 6. And I have to convert this mass into kilograms. I'm gonna rewrite one microgram, negative 6 gram, into kilograms. So I have 110 to the negative 6, and then I'm gonna add kilogram. So to cancel the kilo that I just wrote, I have to write negative 3. So together, kilo and negative 3 cancels. So actually this mass is equal to 1 times, I should say here 1 times. So it is 1 times 10 to the negative 9 kilogram. And when they give you this type of a question, they usually ask for the rest energy, and the rest energy is the mass equal to mc squared. So the mass is 10 to the negative 9 kilogram, and times c squared is 310 to the 8 and all of that squared, which is 910 to the 16. So the energy is equal to 910 to the 7 joules, or if I want to convert this into electron volts, and 1 electron volt is equal to 1.6 10 to the negative 19 joules. So if I want to convert, I do not know how many electron volts is going to be 910 to the 7 joules. So I'm gonna use it as a proportion, and I'm gonna cross multiply this. So then my energy in electron volts is gonna be equal to x times 1.6 equals to, maybe I will write it down this way. So I have x times 1.6 10 to the negative 19 is equal to 1 electron volt times 910 to the 7. So if I want to see what my answer is going to be in electron volts, I have to divide this number by the electron volt, by the electrons. So x is equal to 910 to the 7 divided by 1.6 10 to the negative 19. So my answer in electron volts is going to be equal to 5.625, 5.625. And that is times 10 to the 26. So 10 to the power of 26 electron volts. In this question, they say a photoelectric experiment performed above threshold. That means the energy of the photons is large enough to pull out the electrons, to use the energy for the work function, and then for electrons to have kinetic energy. And as the intensity of the incident light increases, which of the following is true? And then they give you options. So when the intensity of the light increases, that means all of the light that is coming still has the same amount of energy. The photon energy is still the same. What is increased is by how many photons are coming, but every single one of them is still carrying the same energy. So, and then the choices they give you, the stopping potential for the ejected electrons increases. Let me write this formula for you. So this is the energy of the photons, which is Planck's constant times the frequency, and that is equal to the work function plus the kinetic energy maximum. And the stopping potential energy is the energy of the electrons. So this is how much energy you have to stop the electrons. This is the energy that is coming, and this is the energy that is going to be used to pull out the electrons. So just because I increase the intensity of how many photons are coming does not mean that my kinetic energy of the electron is going to increase. So the stopping potential cannot increase. So that would be not an answer. The next choice I have is the number of the electrons ejected increases. So if I have a surface and before I had maybe 3 photons coming, but every single one of them had the same energy, and now intensity increases, that means I have more photons coming with the same energy. That means if before I would bombard out of the surface 3 electrons, now I'm going to bombard out of the surface 5 electrons. So that could be an answer. So the next one, they say the de Broglie's wavelength of the ejected electron increases. It's not, because the kinetic energy does not increase, because the initial energy of the photons did not change. So the work function still the same for this metal. So kinetic energy did not increase. That means the electrons do not carry more energy than before. Then the wavelength is not longer or shorter. And then the number and energy of the electrons ejected are not affected. The number is affected because there's more photons coming, more electrons will be bombarded out, and the kinetic energy of the ejected electron decreases. That is not true. It stays the same because the energy of the photons stays the same. So the intensity increase, that means more photons. More photons means more electrons that will be pulled out of the surface. The answer for this question would be a B. For the next question, they say a photoelectric effect experiment performed with a fixed light intensity is producing ejected electrons. As the wavelength of the incident light is continuously increased, which of the following is true? So the wavelength of the light that is coming is increased. So if I have the surface and the light that is coming has certain wavelength. So if you have the velocity, which is the speed of light of the photons, and you have the wavelength times the frequency. So if the wavelength is increasing, the speed of light cannot change. So if this one is increasing, then frequency is going to be decreasing. So that means if I am increasing the wavelength, I am decreasing the frequency of the incoming photons. If I am decreasing the frequency of the incoming photons, that means after the energy is used to pull out the electrons, for lower frequencies, there's going to be less energy left for the kinetic energy of the electrons. So these electrons, when the wavelength of the incident light increases and the frequency decreases, there's going to be less kinetic energy for each electron after they're pulled out. So let's see what they ask us. They say the stopping potential for ejected electrons increasing. No, because if you have the energy of the electron is equal to, or photons, coming photons is related to the frequency, you have the work energy plus the kinetic energy of the electron maximum, which is the stopping energy. This one is the energy of the photons, and this one is the work function. So if I they say the stopping potential of the electron is increasing. The stopping potential cannot increase because the kinetic energy decreasing. That means the stopping potential is also decreasing. Then the energy needed to stop the electrons. The number of electrons ejected increases. If the same amount of photons are coming, then ejected electrons, the same amount is ejected. The number of energy of the electrons ejected are not affected. The energy of the electrons ejected is affected. It's going to be less because the frequency is less. The electrons ejected will remain constant in number until a sudden stoppage. So what this part means, that as you were, like you can see that they're saying over here, the wavelength of the incident light is continuously increasing. So if the wavelength of the light is continually increasing, the frequency is continually decreasing. If the frequency is continually decreasing, then the energy of the photon can get to the point where it doesn't have enough energy to pull out the electron from the surface of the metal, and all of a sudden the electrons will not leave the metal, and there's going to be no electrons anymore. So this could be the answer. And then the de Broglie's wavelength of the ejected electron decreases. The kinetic energy is decreasing as the energy of the photon is decreasing. So if the kinetic energy is increasing and we rewrite it as Planck's constant times the frequency, so this part is decreasing. And here I have the speed of light over the wavelength. So actually the wavelength is increasing because the energy is decreasing. If this is a constant and this is a constant, then the wavelength is actually increasing. So the only answer in this case would be a D. I really like this picture from physics.info. So this was our fourth video on quantum physics, or the beginning of quantum physics, the basics of quantum physics, where I spoke a little bit about photoelectric effect history and theory. And thank you for watching this video, and I hope I'll see you in the next one. And our fifth video might be the last one for quantum mechanics for AP Physics 2.